Jiang, could you start?
Thank you, Professor Kim, for the nice introduction. And it is my honor to be here to talk a little bit about mooring design for floating wind turbines. And good morning to everyone in Europe, and good afternoon to everyone in Korea and East Asia. And this talk will deal with different topics related to mooring design, but at a relatively high level. So I do not delve into a lot of details of research aspects, but if you have interests or inquiries, please feel free to interact with me or discuss with me after the talk. Okay, and I'm usually quite excited when I talk, so I can talk very fast. So if there's anything unclear, please feel free to raise a question in the chat or ask. Okay, I hope that I will be able to slow down a little bit during today's talk. So first, one slide about my university. My university in Norwegian abbreviation is called UiA, University of Agder. We are located in southern Norway. As you can see here, there are various big cities identified on this map. And we have two campuses, one in Grimstad and the other in Kristiansand. And my Department of Engineering Science, is located in Grimstad, which is a very beautiful city, relatively small city, wonderful place to visit, especially during the summer. If you have ever been to Norway, you would know that the capital is Oslo, and we also have major cities like Bergen, Trondheim, Stavanger, and Tromsø in the north. So here's an outline of today's talk. First, I will give you an overview of offshore wind technology, in case some of you are not familiar with offshore wind. Then I will take a step further to discuss a little bit about design of mooring systems, how to design, what does the design involve, etc. Then I will briefly review some of existing mooring designs of non-commercial and commercial wind projects. Then we'll take a look at a few innovations when we talk about a floating wind farm, right? How to do some cost-effective mooring design. This is a major challenge that the industry is facing. Finally, a few concluding remarks. So maybe many of you already have already heard of this. The world's first offshore wind farm, it is called Vindby. This first offshore wind farm was located off the coast of Denmark. It was commissioned actually in 1991 and decommissioned in 2001. At that time, the water depth is very shallow, only 4 meters. And the wind turbines are relatively small compared to the modern day utility scale wind turbines. So each wind turbine only has a power capacity of 450 kilowatts with a rotor diameter of around 35 meters. Okay, so these 11 wind turbines form the very first offshore wind farm in the world. And this marks the history or the inception of the offshore wind industry. You may laugh at the scale if you compare it with today's large megawatt size wind turbines, but this is actually a great achievement for our industry and for society. And the traditional wind turbine has 3 blades, and this is a typical Danish design. This is the dominant type of wind turbine when we talk about wind turbines today. But alternatively, you can also find vertical axis wind turbines or even airborne technologies, which I do not focus on in today's talk. When it comes to world's largest floating wind farm, this farm has already been commissioned in Norway. This farm is called Hywind Tampen floating wind farm located in the North Sea. This wind farm consists of 11 8-megawatt SPA floating wind turbines. So the foundation type is SPA. This wind farm is used to power offshore oil and gas platforms. So the electricity produced has been directly used to power the operation of platforms. You may have heard of the Hywind Demo project, right? Hywind Demo was commissioned in 2008, and it was taken over by Zephyrus these days. This is world's first SPA floating wind turbine. Actually, the idea of Hywind can trace back to early 2000s, where two engineers of Equinor came up with the idea, and then the first demo project was realized in 2008. This Hywind Tampen is actually the third floating wind projects for SPA floating wind turbine in Norway and in Northern Europe, I would say. The first one is Hywind Demo. Second one is Hywind Scotland with only 5 wind turbines. And this Hywind Tampen marks another milestone for the Hywind history. Different from the previous two Hywind projects, this time Equinor adopts concrete platforms as the foundation for the SPA. So this is quite unique this time. This wind farm is still in operation, so we are very excited to see what will be published if there are any research-related outcomes. Taking a look at the evolution of the offshore wind technology, we know that the first concept of floating wind was originally proposed in 1970s by a professor at MIT. The professor is called Dr. William Hieronymus. And the idea was introduced then, but actually the development of floating wind did not start until early 2000s. As I mentioned earlier, Hywind Demo is a milestone in the history of floating wind. And today we have witnessed many floating wind projects around the world, many in Europe, some in East Asia, also quite a few off the coast of the US and China. So there are various types of floating foundations, including SPA, semi-submersible, and very few on tension leg platforms, which we will come back to later, very briefly. And so far, you can see here, semi-submersible foundations with a relatively slow draft is a very popular and dominant technology for the foundation of floating wind. When we look at important research questions for the offshore wind technologies, what are they? Many people are wondering about the maximum rotor size and power rating that we can eventually achieve and the industry can see in the near future. The trend is we are seeing larger and larger wind turbines with huge rotor sizes. But is there a limit? This is question. This is a big question that we are going to face. But I don't have an answer to this. Where jacket or monopile foundation dominated the intermediate water depths, we all know that for very shallow water depths, less than 30 meters, monopile foundation is dominating in the market. But if water depths increases more than 50 meters or approaches 100 meters, will monopile foundations still be the preferred option? Monopile are very easy to manufacture and can be produced at relatively low cost, but they can also experience quite large hydrodynamic loads if the water depth increases further. On the other hand, jacket foundation use slender elements so that they are less prone to wave excitation. But the storage, manufacturing, and the installation can be quite cumbersome compared with monopile foundations. So this is also related to the third question that I mentioned here. But this question will concern the floating foundation, right? So we know that spar foundations are very good for rough environmental conditions, typical of the North Sea. And semi-submersibles are very good for installation and maintenance because of their shallow draft. And they can be easily towed and maintained and installed at a low cost. But which floating foundation will eventually occupy the market? This may very well be dependent on the site location or the country or sometimes political preference. Which mooring system will be most cost effective? This is also a big challenge to the industry these days. Although moorings have been widely applied in the offshore oil and gas for many decades, still, for floating wind industry with much less profit margin, how can we design and maintain mooring systems in a cost-effective and safe manner? This is a huge challenge that we are facing. How can we install and inspect offshore wind turbines? Because we know that many of the offshore wind turbines are installed in remote places. How can we install them with low risk and with little human intervention, preferably using robotic technologies or drones? This is a very interesting research area that many people are looking at. And what will be the share of the emerging technologies like airborne wind energy? Many people have seen kites, right? So the basic idea of airborne wind energy is that we get rid of the foundation. We do not produce wind at ground level. We produce wind at high level, high altitude level, such that we can make the efficiency of the production much higher. Because we know that for conventional three-bladed wind turbines, it's only the outboard 1/3 part that is effective in producing lift and drag forces. These are the big questions I have off the head of my head, but these are also interesting questions for you guys to explore in future. If we do a forecast of global energy development, we see that the IRENA forecasted that wind and solar will take a large share in the global renewable energy portfolio in years to come. But personally, I do not trust those forecasts. I think today's geopolitical situation has been very complex. It's really difficult to say what will happen for renewable energy investment in the near future. If we talk about a offshore wind turbine, so there are different terminologies. We all know that the rotor blades, these are the three-bladed thing, right? So this is the upper part of a wind turbine. A tower and rotors, usually they are produced by dedicated manufacturers, while the substructure refers to the highlighted part in this graph. The foundation, including the offshore, including the mooring lines. This part can be called substructure. Although sometimes there are also different definitions of the term substructure. We know that for relatively shallow to intermediate water depths, then the substructure type of monopile or jacket are quite prevalent. But it's also believed that when water depths exceeds more than 100 meters or more than 150 meters, then floating foundations are the preferred option. I show you tension leg platform, spar buoy, and semi-submersible here. So as you can see here, tension leg platform have vertical tendons that provide large pre-tensions. So it is these vertical tendons that will make the system very stiff and prevent it from moving, from having large offsets when subjected to wind and wave loads. That's a unique feature of tension leg platforms. But also because of the large pretension of those tendons, the mooring and anchoring costs can be prohibitive. That's why there are very few commercial projects on tension leg platforms. Spar buoy, this is simply a vertical cylinder, right? Can be of very simple geometry, easy to manufacture, and the cost of manufacturing can be put quite low, but the cost of installation can be relatively high because of the deep draft of the platform. Spar platforms has a very low center of gravity, while its center of buoyancy is close to the mid of the draft. So it's like it has very good stability in water. Okay, so because of its unique feature, it's difficult to find harbors with very deep water depths, such that we can tow the entire spar platform in an upright position as it is. Usually we need to tow it in a horizontal position, then upend it at the designated offshore wind farm. And there have been a lot of innovations when it comes to installation techniques for spar floating wind turbines. And during my postdoc, I've also spent a lot of efforts in looking at installation methods for spar formations. Semi-submersible, as you can see here, the draft is relatively small. There's only a very little part of the platform that is below the waterline. Okay, so this unique feature makes it possible to install the whole platform with wind turbines at a dry quay. Then we can use tugboats to tow it to a designated offshore site. This feature makes it very possible to install and even maintain the floating wind turbine at a low cost. If something happens to the wind turbine at an offshore site, we can also disconnect the mooring system and tow it back to an offshore harbor for maintenance. But there are multiple designs of semi-submersible concepts of the day. Yeah, so this image is simply a different illustration of the previous one, spar, semi-submersible, and tension leg platforms. I've already mentioned that the tendons of the tension leg platform will provide large restoring forces. So if you look at the mooring tension in those different mooring lines, then the mooring tension of the tension leg platform can be the highest. On the other hand, there are also different designs of tension leg platforms. There are also inclined tendons. The tendon may not necessarily be vertical. They can also be inclined. The so-called tendon leg buoys have also been developed by the IFE Research Institute in Norway many years ago. So there are the different designs for each type of platform. The reason why I mentioned the floating wind platform is that the mooring design will go hand in hand with a floating platform. Right? You cannot really design the mooring system without any consideration of the motion dynamics of the platform and the wind turbine itself. Looking at the restoring mechanism of floating wind turbines, so we can very roughly make a triangle here. So in this triangle, you see 3 points here, 3 corners here. The upper corner is ballast stabilized. Lower left corner is buoyancy stabilized, while the lower right corner is mooring stabilized. Here, I'm talking about hydrostatic stability of the floating platform. That is to say, if we have a certain tilt of the platform itself, what kind of fundamental physical mechanism that is happening to make it come back to its original neutral position, okay? And the reason why I place high wind here at the upper right corner, at the upper corner, is that high wind, as I mentioned, has a very large draft, right? And a very low center of gravity. So the large distance between the center of gravity of the platform of the wind turbine and the center of buoyancy makes it a very large restoring arm. Okay, that's why we place it there. Ballast stabilized, because we use ballast, we use ballast to lower the center of gravity of the whole platform. The ballast can be of various types. It can be scrap steel, They can be also heavy metal, magnesium. So different types of ballast have been used. Buoyancy stabilized. This applies to most of the barge type or semi-submersible type floating wind turbines. They have certain water plane area to provide sufficient static restoring forces when there's a tilt or disturbance for the platform. While tension leg platforms or tendon leg platforms, they have very large mooring tension, right? A large pretension is usually applied, and that's why we call them mooring stabilized. Okay, and such kind of feature makes it also very difficult to install most of the tension leg platforms because the platform itself may not be stable when it is being transported in water. And actually, all types of floating wind turbines rely on a combination of these three mechanisms. So it's not one single mechanism that is functioning to provide the entire restoring mechanism. Okay, because even for a spar platform, there's also a water plane area that is providing the buoyancy-related stability. And even for spar platforms and semi-submersible platforms with relatively low mooring stiffness catenary design, right? So there are still certain restoring forces provided from the mooring system. So we cannot really exclude any of the corner from this triangle when we think about a platform. So evolution of floating wind platforms. So a few years back, this group, Edwards et al., they published a paper reviewing existing floating wind platforms at sea. And so these are the ones that have already been installed or at a project of various technology readiness level. So we can see that there's a variety of concepts when it comes to the foundation design, when it comes to the support of the wind turbine, or even the number of wind turbines, right? So on the up right corner, you see a Spanish design. It's called SciTech technology, which uses a barge to support a wind turbine. So the barge platform is supported on a single point mooring system with a turret, which is also quite interesting. While the lower left corner shows us a TetraSpar platform. This platform is currently operating in the Met Center of the coast of West Norway. Okay, there's a demonstration project of TetraSpar. This is a Danish design pioneered by the Danish wind pioneer Henrik Stiersalt, and he's developing this concept with the idea of modularity and very low installation costs, installation and manufacturing costs. The idea that we can use conventional steel tubes as the basic Lego elements of the foundation, and we can do the mounting, do the installation at the key site, so that everything can be done very at a low cost. And because of the steel tubes can be mass produced, and that makes the manufacturing cost also relatively low. So yeah, it also uses a keel. As you can see here, this red triangle is basically a ballast weight that is lowered to a certain depth, so as to reduce the center of gravity of the platform, such that it can have restoring mechanism of buoyancy, like a spar platform. But it also uses certain steel wires to connect the platform, the yellow part, with the keel. Okay, so these wires may introduce additional degrees of freedom of motion to the system, which is also sometimes tricky. Yeah, so I'm not going to review all of these platforms, but I think this paper is worth reading if you are very much into the evolution of foundation technologies. And there are a few concepts that have been proposed by various Norwegian companies. The very last one, the very left one is the Equinor concept, right? This is the spa platform used by the Hywind Tampen site. So as mentioned earlier, this platform itself is made of concrete technology. As Norway has a very strong concrete industry, so this makes the manufacturing and production of the platform quite advantageous to us as compared to the first Hywind product. In addition, concrete material is less prone to problems like erosion, fatigue, typical of steel material. And and this spa is also relatively shorter compared to the previous spa foundations used in Hywind Demo and Hywind Scotland. And this Odfjell Ocean Wind is also a Norwegian company that proposed a semi-submersible foundation. This foundation is made of steel structure, while Ocean Ventures is also a Norwegian company, actually in Grimstad, in my city. They propose a foundation that is made of steel tubes. So idea of this Ocean Ventures is that we can use a barge to transport the wind turbine. So actually the hollow part below the foundation can fit a barge, a transportation barge. So the wind turbine can actually sit on the wind turbine during installation. But we are very curious to see the future developments of these concepts, whether any of them would stand out in the market in the near future. Okay, then we come to the important part of today's talk, mooring system. I think I've used quite a lot of time so far. Overview of station keeping systems. So we use the term station keeping to mean that we want to keep the offshore platform in position. Okay, this is a very common term if you browse offshore design centers. So mooring system is simply one type of the station keeping systems. Okay, this is a passive system because we do not need to rely on additional motors or burn additional diesel or fuel to keep the system in position. While in contrast, for traditional oil and gas platforms, floating platforms, we also have thruster-assisted or dynamic positioning systems. That means we need to also have thrusters positioned on different parts of the platform in order to provide sufficient forces to keep the system in position. Okay, so when we talk about mooring system, we're considering a passive system. But it's also interesting to mention that for floating wind turbine technologies, I've also seen papers proposing thrusters mounted on floaters to assist the mooring system. There are some recent papers developed by Australian researchers several years ago. So what is mooring? So mooring is a station keeping system, as I mentioned earlier. Mooring transfer the loads. We have the platform and the wind turbine, they are subjected to loads, right? The platform is subjected to hydrodynamic loads due to waves and currents. And wind turbines are subjected to primarily aerodynamic loads, right? The blades have lift and drag forces, while the tower also have drag forces. So these loads are put onto the wind turbine and the platform, but it is mooring system that eventually will transfer the loads onto the anchors. And the mooring systems keep the floater from drifting away under various types of environmental loads. So this is quite apparent to many of us here. Mental categories of mooring systems. So depending on the categorization, we may divide a mooring system into some of the categories I'll show here. So traditionally for oil and gas systems, we have catenary system, which is very common. That is to say, we want to use the gravity or the geometry restoring to keep the system into its to restore the system to its original neutral position when it has an offset due to environmental loads. Taut system, means we have inclined tendons, while tendon system, the tension leg platforms, we have vertical tendons. So this categorization is based on line configurations of the mooring lines. Alternatively, if we divide the mooring system based on weather vaning capability, then we also have spread mooring system and the single point mooring system. Okay, single point mooring system, it means that the whole platform, it can rotate in your degree of freedom. When the wave load, for example, changes from one direction to the other, the system itself can get aligned with the dominant environmental loading. That being said, that we do not need to take the environmental loads. We just make the platform adjust to the dominant direction. So there's a turret system, a turret and bearing that allows the system to yaw freely. Okay, although this is still a passive system. While for the spread mooring system, so basically it is a mooring lines that will pull back the system and the floater to its neutral position. So this is this categorization is based on weather vaning capability. So mooring design is usually very difficult because the floater is subjected to various types of environmental loads. Okay, sometimes the loads are unpredictable. And the loads are acting with the mean force and dynamic forces, generally speaking, right? So especially when we talk about wave loads, there's a large mean drift for very large platforms. The dynamic forces can be of various reasons. It can be of first order forces, it can be of high order dynamic excitation due to second order effects. So the dynamic forces are very hard to deal with usually. It's the dynamic forces that lead to cyclic loads in the moorings and often fatigue problems associated with that. Design of mooring system. So I'll give you a overview of the design considerations, and then we can take a look at different aspects. Looking at the design spiral of a floating wind turbine, so there are many considerations that we need to take into account. The floater design, hydrostatics, mooring design, cable design, the array layout, as well as the economic aspects related to power production, right? Layout optimization. So there are many things that we need to consider. Also, social and environmental impacts. This is also quite important for many societies because there could be very strong resistance from fishermen, and we do not want to incur large impact on the environment even after the floating wind project has been decommissioned. Site assessment this is usually carried out at a very early stage. We need to know the potential wind resources as well as meta-ocean conditions. What will be the dominant environmental loads, right? The dominant wind direction, wave direction, current loads, etc. So there's a whole bunch of considerations that we need to account for at the design stage. And this mooring design is just one piece of the spiral, and there can be several cycles that we need to do. Okay, it's not that we just do the design, you one fell swoop and it's done. It's not like that. We need to have a lot of iterations with other different tasks. What is mooring design? I give a definition here, but this is my own definition. Mooring design involves the selection of design parameters, that is to say, various mooring components, like composition, to say how do we place different compositions at, and what will be the ideal length, ideal weight, for example, and what will be the layout of the mooring, right? For a single platform, we're talking about the total. The layout may be the total number of mooring lines and the angle between individual lines, while for a floating wind farm, the layout can be more complex, which I'll come back to later. And as to date, there's no proper definition of the mooring design at the farm scale because this is still very new to the industry. We want to do this at a reasonable cost, but sometimes it's not simply the cost that is driving the final selection. We all know that, right? So this is not a very simple design optimization problem because there are various interests that we need to take care of. And when it comes to mooring design, lots of expert knowledge must be involved because we know that some of the solutions do not work some of the solutions work. And actually, it is this part that has been very challenging to junior mooring designers. It's not just a very simple design task because of the complexity of the picture. If we look at the life cycle of mooring system, so the mooring design is primarily done at the bidding phase. So we need to have a preliminary design in order to make an estimate of the cost. Then at the project phase, we need to have detailed design so that we design the system, we get proper dimension as well as land composition. Then, but eventually, if a mooring system fails, then we also need to redesign the system, right, and repair the system if necessary. So these two yellow part is just the stages where primary mooring designs are carried out, but does not mean that we do not do any further designs during its entire life cycle. When you look at the restoring characteristics of a mooring system, usually we are most interested in the so-called fair lead position. Fair lead is the position where the mooring line is connected to the floating platform, okay? So if you look at the figure here, so it is this upper point that is called fair lead, okay? So sometimes we can use a single degree of freedom system to describe the behavior of this fair lead. But we know that the fair lead tension prediction is a very complex thing because the spring stiffness here, they are not constant when the fair lead moves, right? Some of the restoring come from the geometry due to the change of the line shape for traditional catenary lines. But when the offset of the platform is large, then it will be the elastic stiffness due to the extension of the lines that is dominating, as you can see here on the right part of this figure, dynamic extreme tension. So this geometrical effect Kg will disappear. But in addition to the stiffness effect, there's also damping effect on the mooring lines. If you do a decay test of wind turbine mooring, then you can easily see the effect of drift damping on mooring lines. So for tension in the platform, so if we look at the restoring characteristics, then it will be dominated by the elastic part of the mooring tendon because the lines are always in tension, right? So there's very little geometrical effect due to the weight of the lines. Typical natural periods of a single floating wind turbine. So these are the natural periods for the system with wind turbine as well. I'm talking about the rigid body natural periods of a platform. Okay, I'm not talking about the flexible natural periods of the blades, etc. So there are only 6 degrees of freedom for a rigid body, surge, sway, and these are the modes dominated by mooring systems because it's only the mooring system that is providing restoring the horizontal plane, right? While heave, roll, pitch, and yaw, these are degrees of freedoms that are usually governed by other factors like the water plane area. Yaw, especially for spar floating wind turbine, then is also mooring that is governing because the original design of high wind demo has a delta line configuration that is providing large yaw stiffness. So this table is just a very brief overview. The main idea is to avoid resonant excitation of wave forces at the main wave excitation regions. That is to say, wave excitation between 5 seconds and 40 seconds. We want to design the mooring system such that the platform will not get excited in the resonant region. That's the fundamental principle when we consider the natural periods of a floater. Functional requirements of mooring system. We want to limit the horizontal offset of floating structure to an acceptable limit. Okay, so why do we want to keep it to an acceptable limit? Because it is not the mooring system that gives this requirement. It is actually other components, for example, power cables, that may not be able to tolerate very large offsets. That's why we want to keep the system within a certain motion range. Okay, and the mooring system will take the mean offset and the low frequency motions. But for the wave frequency motions, these are usually, we can regard them as quite high frequency part. So we do not really let the mooring system take the loads. The platform is free to move along with the first order excitations. It is worth mentioning that the mooring system is a safety critical system. That is to say, if we lose the mooring system or if certain parts fail, then the whole system may be at hazard. We do not want to lose a floating wind turbine, let alone a floating oil and gas platform, if the mooring system fails. So that's why at the design stage, we need to make sure that we have a sufficiently low probability of failure. When it comes to mooring materials, I will only very quickly touch upon them. So traditionally, chain is widely used. Chains are very heavy and can provide a very large restoring stiffness. While steel wire ropes are relatively lightweight compared to chain, they are also widely used in offshore oil and gas. And the steel wire ropes are also relatively cheap compared to chain because they are much lightweight. But in recent years, synthetic fiber ropes have been increasingly applied in offshore wind projects because these ropes are very, very lightweight and even more cost-effective than traditional material. But the challenge is the material property uncertainty related to such material, right? So significant testing is required before we can put them into use. There are a few ongoing knowledge building projects in Norway related to fiber ropes. So this is a very important and interesting development for mooring design. While other components like clamp weights, shackles, buoyancy elements, they may change the mooring geometry and provide additional functionality if needed. But some clients may not want to have those components. So mooring design sometimes also involve very close dialogue with the potential clients. General framework for mooring design is something that I want to present. First, we need to look at the design basis. What will be the starting point for our design, right? So the meta-ocean conditions, the extreme wind and wave conditions, the ocean bathymetry, water depths, as well as past experience. So this is something that we bring along with us when we start our design. Design constraints, as I mentioned earlier, there could be constraints related to flow to natural periods. There could be requirements by clients. There are also constraints due to rules and regulations. We need to satisfy the basic design requirements for mooring safety, right? We need to make sure that we have sufficient capacity for the chosen mooring configuration as compared to the load effects. We also need to satisfy the structural integrity. This also go hand in hand with rules and regulations. Sometimes we also need to have compatibility with other subsystems of a floating wind turbine. Design methods, this is something that's also widely applied in design of other types of civil engineering structures like bridges or buildings, right? Traditionally, we have deterministic methods, but in the last century, people have developed semi-probabilistic methods. So basically, the partial safety factors proposed by design standards can be used to facilitate efficient mooring design. So we only need to use those partial safety factors to achieve sufficient safety. But to calibrate those partial safety factors, sufficient efforts must be spent beforehand, right? Applying structural reliability methods. And the design parameters, as I mentioned earlier, there's a variety of parameters that one can take into account depending on the availability of components at disposal. Design of mooring lines, we need to check the so-called limit states. Limit states can be formulated as mathematical formulations, right? It can be the borderline between the safe region and unsafe region if we divide the total domain into two regions. So according to design standards, there are three dominant limit states. Ultimate limit states, we need to ensure that mooring lines do not break. Accidental limit states, in case we have line failures or very extreme environmental conditions like those of 1,000-year occurrence. Failure fatigue limit state, this is oftentimes a very important consideration because many of the mechanical components fail due to cyclic loading. In addition, there could be other limit states that have not been explicitly formulated by design standards, like serviceability limit state, right? Comfort. So these things have not been looked into very much in the past. This is the flow chart for the floating wind turbine mooring design process. When we have initial design inputs, we carry out preliminary design. Usually, mooring design involves numerical coupled analysis, which is very time-consuming. So that's why at the preliminary design stage, we often only carry out screening analysis according to the ultimate limit state to see which types of choice will fit our basic needs. Then if eventually the client decides to go ahead with that option and we get the bid, then we can carry out more detailed design, checking all the limit states of our chosen mooring system. And sometimes we also need to carry out model tests for the entire system in a wave basin to calibrate our numerical model. This is often quite necessary. And if the classification society like DNV, ABS, or BV approves our final design, then we can regard the design as complete. Okay, so in the following, I'm going to review some of the existing mooring designs of offshore wind projects. So there have been many mooring designs as well as floating designs at this stage. In this figure, we can see 8 picked designs, starting from OC3 high wind in 2010 to the late Volturnus S design in 2020, made by University of Maine. So there are many academic designs, and it's very interesting to see the use of these academic designs because this openly available data make it possible for researchers and academics to model and analyze wind turbines. But I have to say that usually the design of the mooring systems of those academic projects are less detailed, and they have not really considered all the limit states. And oftentimes the moorings provided can also be unrealistic. For example, for the OC3 high wind project, they only use a 90mm chain for the entire mooring system, right? So because the purpose of those non-commercial projects is to provide a basis or reference wind turbine, so they have not really looked at the feasibility of mooring systems. For the Volturnus design, they have only looked at the ultimate limit state. They have only done very limited design load cases. On the other hand, we also have mooring design of commercial floating wind projects. So those designs have been certified by design classification societies, and they are also an evolution of the design of the material chosen. As you can see here, high wind demo uses 3 mooring lines with a combination of Y and chain material, while wind float projects used HMPE, which is a type of thermoplastic material with a combination of chain, and synthetic fiber ropes are also being increasingly used in latest projects like Floatgun, the famous French project with a damping pool for the floating platform. So if I ask a question, what mooring system is what mooring is used for high wind Scotland? This wind farm with 5 floating wind turbines. Can anyone answer me? Actually, a full chain design is used for the high wind Scotland. So the Equinor resorted to a quite conservative design at that time. They did not put into use any new material. So there are trends and observations that I would like to highlight here. The mooring designs from academic projects are oftentimes simplified with limited documentation of design checks, while the commercial projects demonstrate a broader spectrum of water depths and mooring designs. But unfortunately, many of the design details are not really released to the public domain. Catenary systems still dominate the cases, while single float mooring system is still being tested at an early stage. So these are the main observations I have. Okay, then let's move to the exciting part to take a look at a few innovations at farm scale. When we talk about mooring innovations, so we can think about many things, right? We can think about the use of innovative mooring components, right? Maybe you will put into use novel material like polyester, nylon, even polymer systems that can absorb certain type of peak loading. In this talk, we are going to primarily focus on layout and configuration of the mooring systems. So I'm going to talk about shared mooring systems. So the basic idea of shared mooring system has been proposed quite a few years back. So Matthew Hall at Unreal is a pioneer of this idea. So if you look at the paper published 2019, they proposed a few concepts for pilot scale floating offshore wind farms with shared mooring. But shared mooring is a very broad term. Here, I want to further categorize the shared mooring systems into 3 different types of systems. The first type is called a shared mooring line system. That is to say, we use mooring lines to connect individual wind turbines together. Okay, so in this slide, you see 3 configurations, right? So the layout on the left has only 2 wind turbines with 1 shared line and 4 anchor lines, okay? Or sometimes we call it single line because this line connects the wind turbine to the seabed directly, okay? While for the configuration in the middle, we have 4 shared lines and 4 anchor lines. While for a larger scale floating wind farm, we may have multiple shared lines and multiple anchor lines. So my PhD student studied a prototype floating wind farm with a shared line during his PhD. So if you look at the illustration on the left, you see a configuration that consists of 2 5 megawatt spar floating wind turbines with 4 anchor lines and 1 shear line. So this is the simplest configuration of a shear mooring system, right? With only 2 wind turbines. But still, for such a system, there's a raised degree of complexity because we are coupling 2 individual wind turbines together, right? So there's a strong coupling between the 2 wind turbines. For those of you who know structural dynamics, we know that we can linearize the stiffness of the system, especially due to the mooring lines, right? We can add contribution due to shear line and the single lines, then we can assemble the stiffness matrix. If we only look at the rigid body motions of the spars, then we can take a look at this right figure, which shows us, 12 modes here. So for certain modes like this row 1, so the 2 spars, they can move relative to each other. These are the coupled modes. So these coupled modes can actually raise concerns, right? If we have dynamic simulations. Because as I mentioned earlier, for single float, we want to have natural periods quite away from the dominant wave excitation regions. But for such couple modes, those natural periods may fall within the region. So they may raise concern if we do not have sufficient damping in the system. So I'm not going to talk a lot more about the numerical analysis of this prototype floating wind turbine. I want to spend a few minutes on the experimental test of the shared mooring line system that we did in collaboration with UP Madrid as well as CHIPA in Spain. So we carry out this model test of 2 spar floating wind turbines with 1 shared line and 4 single lines in Madrid back in 2022. We look at these 2 floaters, okay, without any wind loads. So this is only wave only case. And the scaling ratio is fruit scaling, so with a ratio of 47, and we modeled two wind turbines with a mass distribution of the original OC3 wind turbine, and we measure the fairlead tension at the single lines. The single line has 2 fairleads, right? As well as the shear line has 2 fairleads, while the single lines has also 4 fairleads. We measure the mooring tension at those fairlead positions. We look at 2 environmental conditions. If you look at HS, which stands for significant wave height, and TP, which stands for spectral peak period, we look at 1 operational condition and 1 extreme condition, typical of the North Sea. And we also look at different options for that shared line with and without the effect of a clump weight in the middle, because previously we observed certain snap loads that occur in the shear line. So we want to see if we apply a clump weight, whether this will be effective in removing this, in alleviating this effect. And then we measure the motion of spar 1. Okay, only the 6 degrees of freedom motion of spar 1 was measured, but not spar 2. The reason was due to the limitation of the test facility at that time. For such kind of multi-body system, if we're going to test them, there could be challenges, sometimes unexpected. For the main body of the spar, we use PVC material. For the ballast, we use solid lead, solid lead, and we also have good instrumentation of the system, right, which I do not show you here. So in this slide, I show you a video of the tests under irregular seas. HS equals 12.77 meter and TP close to 16 seconds. So this corresponds to an extreme environmental condition. Okay, let's watch this video together, where you can see the movement of the 2 spars. So actually you can see here, 1 spar is on the left, the other is on the right, relatively small. So irregular waves are generated, so they're moving. Yeah. We cannot really see the shear line here, and we cannot really see the movements of the single line either, but we do have underwater camera that capture their motions. Okay. Okay, so I'll talk very briefly about shared mooring lines, and if you're interested, you're encouraged to read our publications. Yeah. Also, in addition, we also have shared anchor systems. Broadly speaking, this is also part of the shared mooring systems, right? Because the mooring are shared in a way. Because in this figure on the left, you see that the anchor in the middle is larger than the one on the side, right? So the 2 mooring lines are connected to each other via this shared anchor. Actually, this is a very economic option, because then we reduce the total number of anchors, right? So actually, this option has already been applied. This innovation has been applied in the high wind tempered wind field. Okay, so if you look at the figure on the right, I show you the rough sketch of the high wind temper wind field, where you see a number of shade anchors. Yeah, for example, A16, A13. These are the labels where I mark the shade anchors. Shared buoy system. Sometimes we can also use a buoy to connect wind turbines together. So the wind turbines are not directly connected by lines. They are connected with a middle point, that is a buoy. So these buoys are tension-legged buoys. Actually, they can be installed at a relatively low cost because they only need to have one tendon, right, anchored to the seabed. So this is a minimum example of a shared buoy system. The buoys, if submerged from the water depths, submerged at a certain water depths, then there will be very limited wave excitation on the buoy itself. Okay, so the idea of shared buoy system is that we reduce the stiffness of the mooring system. So the system will be much more compliant than the system before with conventional catenary line, for example. So they could experience larger offsets, but the mooring loads, on the other hand, would experience a significant reduction. That will be the advantage. So there's no free lunch in the world. If we achieve an increased performance in one thing, there could be certain other unexpected effects that we do not want. So the shared buoy concept actually was originated from this Norwegian company called Sema. They proposed the idea of honey mooring in order to have a hexagonal honeycomb-shaped floating wind farm layout. And my PhD student and I, we looked at the, again, prototype floating wind farm with only 2 wind turbines and one shared buoy. And then it was found that, the system has very increased compliancy with a huge reduction in the extreme mooring tension, which could be advantageous to a certain point. But on the other hand, the power cables need to be challenged. Yeah, finally, some concluding remarks. So I want to mention that safe and cost-effective mooring designs are critical to the floating wind industry. So how to have a good trade-off of these two aspects will still be a challenge to many. And I've also identified a few research areas that can include intelligent design tools, design of hybrid mooring system, co-design with other components in a floating wind farm, design for floating wind farms with other marine renewable energy facilities. And the first point relates to intelligent design tools. As I mentioned earlier, it will be very hard for a junior designer to design mooring system. So how to incorporate expert knowledge bank with some AI-assisted tools, this can be a very interesting aspect to explore in future. And the very last point I would like to mention that coexistence of floating wind farms with, for example, PV panels can be a very interesting topic to explore if we can reduce the total cost of mooring system and infrastructure. Just a very little teaser in AI in estimation of mooring dynamics. This is an aspect that I've also looked into when it comes to structural health monitoring. But I think AI can also be used in reduction of design load cases of mooring systems. Right? If we manage to use AI for design optimization, this can be also a very interesting area to explore in future. So a number of references that I've included in my talk. So the major part of my talk has been based on this recent review paper that is highlighted here. If you're interested, you're welcome to read it. And yeah, so that's it. And if you have any questions or collaboration opportunities, feel free to reach out to me. And every year we have in Europe, we have a call called Marie Curie actions for recruiting future young talents in research, postdoc fellowships with a deadline in September every year. The call will be open very soon. So if you are interested to discuss opportunities, you're more than welcome to reach out to me. Yeah. So yeah, that's it. If you have any questions, feel free to interact with me. I will still be here for a while. Okay, right? Yeah.